So far, we've talked about two angles that intersect with arcs. The first one we talked about was the central angle, and then we talked about inscribed angles. We're going to talk about three other types of angles today. The first one we're going to talk about is the angle that is made by a chord and a tangent. So we were looking at angle ABC, and the question that we're going to ask is for angle ABC, how does it relate to the arc BC? And to do that, we're going to look at an interactive one. So here we have a version of it, and I'm going to zoom in so it's a little easier to see. And what we're going to say is, imagine we have some point B2 on that diagram that is somewhere between B and C. And we can draw a segment to that point, and then we can imagine that angle. Now, we know that if this arc length was between B2 and C was 60 degrees, we know that this is 30 degrees. The angle made by that arc is 30 degrees because it's 1/2. It's about 30. You know, it doesn't look exactly like 30, but it's about 30 because it is subtending that arc, and therefore it is half the measure of the subtended arc. If we take this and move it, and we slowly go closer and closer and closer, look what happens as B2 approaches B. As B2 gets closer and closer and closer to B, we'll notice that the angle is basically the full amount of that arc. And as this gets closer and closer, and maybe eventually when it eventually hits B, effectively it gets to the same measure, 70 degrees. So if the arc BC, the measure of arc is BC, you have kind of an inscribed angle here, but it's not really inscribed anymore now because it's no longer being made by two chords. I mean, when B2 is out here, the angle is being made by two chords. But this chord between B and B2, as it gets closer and closer and closer, it actually becomes the tangent. And therefore, what we can say is that an angle that is made by a chord and a tangent is actually going to be 1/2 of its subtended arc. So we can say that the measure of angle ABC is going to be 1/2 the measure of arc BC, for the same reason that you have an inscribed angle. For an angle that is made by two chords, this gets a little difficult because this center, to be clear, this center doesn't necessarily have to be the center of the circle. This point, this intersection point of the two chords, isn't necessarily the center of the circle. To figure out this one, it's actually a little bit more challenging of a proof, and I'm not going to prove the next three, but I am going to prove this one for you briefly. So if we said, well, let's just create something there, and we just created another chord that's just going to help us, because it's going to help us see two other angles. Call that angle 2 and call that angle 3. Angle 2 is an inscribed angle, and the arc that it subtends is AD. Angle 3 is also an inscribed angle, and the arc that it subtends is angle 3. Is arc BC. We know that angle 2, the measure of angle 2, is 1/2 the measure of arc AD. We know the measure of angle 3 is 1/2 the measure of arc BC, because they're both inscribed angles. What we also know is that we have a triangle here. I want you to see this triangle. And what we learned way back in October is that an angle, the third exterior angle of a triangle, is equal to the sum of the measure of the other two interior angles. Remember when we did exterior angle way back in October? So therefore, what we can say is that angle 1 must be equal to the measure of angle 1 must be equal to the measure of angle 3. And therefore, using substitution, and if we take out the 1/2, we factor out the 1/2, That's a fancy way of us saying that if we have an angle that is made by two chords, this angle 1 is made by the intersection of two chords, that the measure of this angle is the average of the two arcs that are created by that angle. Just to be clear, folks, it's important for you to see that these are vertical angles. This also is angle 1. So angle 1 subtends both arc BC and AD. So the measure of angle 1 is effectively the average of the measure of arc AD and BC. The last ones that we're going to talk about are actually angles that are on the outside of a circle, but they are made by either two secants or two tangents, or a mixture of a secant and a tangent. This first example, I want you to notice that CD is a tangent and CA is a secant because it connects the circle twice. And I'm not going to do the entire proof. If you want to see the proof, there's actually proof in the book. It's exercise 10 in chapter 9.6. However, I'm just going to show you the answer. There's two arcs that are being created here by this angle 1. There's this arc on the outside, which we're going to call the larger arc, and this arc on the inside, which is the smaller arc. And the formula for this measure of angle 1 is going to be 1/2 the measure of the larger arc minus the measure of the smaller arc. The same holds true. This formula holds true whether using secants or tangents. So for this next example, we have two tangents. FG is a tangent and FE is a tangent. And again, we have two arcs that are created by angle 2. We have this arc, which is actually a major arc, or the larger arc. I'm just going to call it the larger arc. And we have this arc, which is the smaller arc. And every single time, the measure of the angle, regardless of whether it's secants or tangents, is going to be the measure of the larger arc minus the measure of the smaller arc. And lastly, we have two secants. LJ is a secant, LN is a secant. We have a larger arc that is created by angle 3. We have a smaller arc that is created by angle 3. And again, the measure of angle 3 is the measure of the larger arc minus the measure of the smaller arc. That should have been an N. So to quickly summarize though, it's important for you to notice that angles on the outside, notice that angles L, F, and C are all on the outside. And therefore, if they're on the outside, we are subtracting the larger arc minus the smaller arc. All three of these examples have angles that are on the outside, which is different than the problem we did here, where the angle was on the inside. If the angle is on the inside of the circle, we're not subtracting, we are adding the two arcs and averaging them. Please notice the 1/2 on all of the examples.